Hello everyone. In this video, we're going to look at the minimum in a rotated sorted array problem. The problem is that we start with an array of sorted unique numbers, then all the numbers in the array are shifted to the right by an unknown amount of times, and after these shifts occur, the array is given to us and we have to find the minimum value in the array. I think the brute force solution is relatively simple. We just keep track of a running minimum while we iterate through the entire array, and in the end, we return this minimum. However, the time complexity of this is O of n, and we can actually do better by taking advantage of the fact that the array was initially sorted, along with the fact that the numbers are unique. I think the thing to notice about our input is that regardless of how long it is and how many times it has been rotated, there's going to be specifically one spot where the sort breaks, and the rest of the array is going to be sorted. So in this example, that point would be here. We can call this point a break point, and for this next example, it would be here. And if we get an example where the array wasn't rotated at all, then the breakpoint would just be at the end of the array. But regardless of where the breakpoint is, it should make sense to you that the element immediately to the right of the breakpoint is the minimum element in the array. In the case of our last example, the minimum just loops back around to the beginning. So our improved solution can just essentially boil down to the fact that we need to find this breakpoint. We can do this in log n time, with a method similar to binary search, using the fact that the array was originally sorted. Let's start our code similar to binary search, with a left pointer and a right pointer, and a while loop which will run until the left pointer goes beyond the right pointer. In the while loop, we're going to set a mid variable to be the middle index between the left and right pointers. Now we can encounter three possible cases. Case 1 is that mid happens to be exactly on our breakpoint. We can detect this case if mid is greater than the value directly to its right, and if this is the case, it means that this is exactly the point where our sort breaks, and it's our breakpoint. To handle this case, we just return the number to the right of the breakpoint, which as we discussed earlier is going to be our minimum. The other two cases are either the breakpoint is to the right of mid, or to the left of mid. Remember that for any case, there's only one breakpoint in the list, which means that there's only one point where the array is not sorted, so to speak. So if the breakpoint is on the right, then that means the left is sorted. This means in terms of our code, we can detect the case where the breakpoint is on the right by checking if the mid is larger than the left. Now we can handle this case similar to binary search. Although we can see between the 31 and the 1 is exactly where our breakpoint is, our algorithm doesn't know that. All our algorithm knows is that it's not to the left of mid and it isn't mid itself, so it's got to be to the right of mid. Therefore, we think of the numbers between left and right as our possible range of candidates. Then we can reduce our search space in half by eliminating the left half and moving left to mid plus 1. Similarly, we can handle the case where the breakpoint is to the left of mid by moving right to mid minus 1. Okay, and that's basically the whole idea of the solution. However, before we finish, there are a few minor edge cases we have to handle. The first is that mid might reach the very end of our array, and in that case, mid plus 1 could go out of bounds. In order to account for this, we need to mod the mid plus 1 index by the length of the list to have it wrap around to the beginning. Another edge case is when the list is just a single element. To handle this, we need to make the first if statement have a greater than or equal to sign. And our final edge case is something like this, and in order to handle this, we can make the second if statement a greater than or equal to. Now let's look at the time complexity. By implementing this mechanism similar to binary search, where at each iteration of the while loop we're cutting the search space in half, our running time becomes O of log n. And one more thing to mention is that there's actually a bit more of an elegant solution out there that looks like this. The idea is pretty much the same, but I just wanted to bring it up at the end of the video because in my opinion our solution is a little bit easier to understand. But this one is definitely shorter and has one less case to check. I'll let you prove to yourself that these two solutions pretty much do the exact same thing and both have log n complexity. With that brings us to the end of the video. This one was a bit short, but regardless, if you have any questions, feel free to leave them in the comments and I'll do my best to answer them. If you found this video useful, please consider liking the video and subscribing to the channel. All the support really helps. Anyway, thank you for watching and I'll see you guys in the next video.